and welcome to CPFD's Getting Started with Virtual Reactor 25.0 webinar. My name is Rosemary Clark, and I'm the Senior Support Engineer for Barracuda Virtual Reactor, and I'll be your host for today's webinar, and CPFD's Sam Clark will be our presenter. We're excited to have this opportunity to tell you about the new features and enhancements included in this version 25.0 release. Today's webinar is being recorded and will be posted on CPFD's Webinars and Presentations webpage under the Resources tab. So if you miss anything or you want to share something you saw with a colleague or a friend, make sure to check that out and share the recording in the next day or two. And as you think of questions during the webinar, please put them into the question panel accessed by clicking on the orange arrow. We've intentionally allocated a significant amount of time to answer questions after the presentation, and audience participation via the question panel will make things more interesting for everyone. And if you've got a question about something, odds are someone else will be wondering the same thing. For people watching this webinar who are new to CPFD software, let me briefly introduce our company. Here at CPFD Software, we're advancing multi-phase simulation and technology for fluid particle systems, primarily fluidized bed reactors. Barracuda Virtual Reactor is our software product that models 3D transient hydrodynamics, heat balance, and chemical reactions in industrial units. For over 15 years now, people have been using Virtual Reactor to improve the reliability and performance of their systems through simulation. For engineers working with already operating units, virtual reactor simulations allow you to look inside the system in a unique way, determine root causes of underperformance, and use virtual testing to reduce the risk of making any changes. And for companies developing new technology, Barracuda can help accelerate and broaden R&D, and then quickly commercialize, scale up, and communicate the unique capabilities of your technology to customers, partners, and others. The presenter for today's webinar is Sam Clark. Sam is the Barracuda Virtual Reactor Product Manager and has been at CPFD since 2008. He works closely with CPFD's development team to design features and capabilities for Virtual Reactor that benefit our customers all over the world. And so I'll turn it over to you now, Sam.
Thanks for the introduction, Rosemary. And thank you to everyone who's joining us for the webinar today. The development team here at CPFD is proud to release Barracuda version 25.0, which has a number of new features that we think users will really enjoy. If you're a Barracuda user, you should have received our release email earlier this morning. If you didn't, please let us know and we'll add you to our email list for future release announcements. Version 25 is available for download on the CPFD support site now, so please log in to download it from the dashboard. You can find more details about all the things we'll cover today in the release guide chapter of the user manual, along with links to the full documentation sections throughout the manual. An area we focused on quite a bit for 25.0 development is wall impact models. In this release, we've added support for enabling multiple wall impact models at the same time, each of which can be specified with its own parameters. For example, if you have bare metal surfaces in one part of your reactor and refractory lining in another region, you can define wall impact models for those different materials and get erosion results for both in the same simulation. Two new wall impact models have been added for this release as well. Liquid accretion is the first one, and Oka erosion is the second, and I'll discuss that one on the next slide. The liquid accretion model can be used to track liquid material accumulating on wall surfaces due to particle impacts. This is useful if your particles are either coated with liquid or if the particles are 100% liquid to represent droplets. For example, this model can be used to identify where liquids from spray nozzles might be coating walls of the vessel. For all of the wall impact models, we've also added the ability to select the region where the model results will be calculated. This can help with organization and visualization of the model results so that only the specific region of interest for each model is active. And I'll show that a little bit in our demo in a few slides. The second new wall impact model that's been added to this release is called Oka erosion, and it has the benefit of providing quantitative erosion calculations. This model is based on 2 papers authored by Oka and others in 2005. The calculated erosion rates are material dependent, so the user can select from one of the predefined options in the drop-down menus for wall and particle materials, or you can define your own parameters according to the Oka form. The output data from the Oka erosion model has units of kilograms per meter squared per year, where the mass indicates how much material has been removed from the wall due to particle impact. To help you quickly visualize the results of the wall impact models, we've added a quick macro panel item in Tecplot for Barracuda. Its name is Walls Impact, and if you double click it, you'll get a view of the walls colored by the results for the first defined wall impact model in your project. If you want to see the results of the other wall impact models, you can double click on the contour legend and then you can select them like you usually would for changing variables in Tecplot. Closely related to this is a detail that can be useful to know about as you start looking at these results in Tecplot. A new zone has been added for the walls in this release. So this is helpful when we visualize wall impact model results because it makes things quite a bit simpler than dealing with isosurfaces or cell blanking, which we had to do in the past to create nice images or animations of wall impact. The quick macro panel item uses the walls zone for displaying the erosion results. And you can also find some other information in that zone, such as wall area. Another feature you'll see in this release is the ability to include hydrostatic pressure at fluid ICs and pressure BCs. This will have the most impact for simulations that involve fluids with relatively high density in the flow domain, and or those that have pressure BCs in vertical orientations. By using hydrostatic pressure for a fluid IC, a simulation can often start more smoothly because the pressure profile at time 0 should be closer to the steady state condition after a hydrostatic pressure profile has been established. For pressure BCs that are non-orthogonal to the direction of gravity, using a hydrostatic pressure profile at the BC can help to avoid artificial recirculation. This can be important for simulations of horizontal pipe flow or for other configurations where the pressure BC spans a significant height in the domain. The equation used for the hydrostatic pressure calculation is shown here. And the important thing to note is that the user specified pressure, which is P0 in the equation, is assumed to be at the center of the specified spatial region for the IC or the BC that you're defining. Another update we've made for the 25 release is to the thermal wall BC GUI layout. We've ported this to a tab-based design for better organization of the inputs and to be more consistent with other BC dialogues throughout the GUI. The location tab has all the controls for selecting the wall locations where the thermal wall BC will be applied. In this tab, you'll also see a new option for selecting location by using a user-defined expression. This control has actually been added to all the BCs, and I'll discuss it more on the next slide. The thermal wall tab in this dialog has the controls for specifying wall temperature and other physical properties of the thermal wall, such as emissivity and resistance. The ability to select BC locations by user-defined expressions is a powerful new feature in the 25 release. The UDE syntax here is the same as for user-defined drag models or chemical reaction rate coefficients, which you might have used in the past. For the purpose of selecting BC locations with these expressions, we've added variables for cell center locations, and those are the CX, CY, CZ that you see listed here. We've also added face centers, FX, FY, and FC, and face normals, NX, NY, and NZ. And so then the expression that you define is used in combination with the other region selection controls, such as the XYZ region box and the direction controls that have always been there for selecting BC faces. And again, this is something I'll demonstrate in a few slides when we go into the demo. The example on this slide illustrates how BC faces can be selected using this new feature to get shapes that would be quite difficult or tedious to define using only the previously available select region functionality. By defining a few equations and using the newly available OR operator, which is the two vertical lines on the last line that you see there, called pipes. If you use those, we can do this sort of flow BC pattern of concentric rings with about 10 lines of code. If you were to select these same cell faces using traditional XYZ Cartesian boxes, it would probably require hundreds of individual BC definitions to achieve a complex pattern like this. Now we'll discuss a couple of new solver options that should help certain simulations to run quite a bit faster. The first is a new option to calculate fluid temperature from the material enthalpy and specific heat using a nonlinear solver. This is a calculation that comes after the energy solver finishes to ensure that the temperatures in every cell are consistent with the calculated enthalpy. This can allow simulations to run at higher time steps while maintaining stability and accuracy. So if your system has large temperature changes during a time step, it's quite possible that you've already been seeing warning messages like this one that's shown on the screen, which say decrease DT, large temperature change in cell. And this has been the default approach taken by the solver for many years now, which is to reduce the time step of the simulation in order to prevent the temperature changes from becoming too large. And this strategy worked, right? It allowed the linear temperature solver that's always been in the code to operate with reasonable accuracy and maintain stability. However, this approach does have the downside that it potentially slows down your entire simulation quite a bit because the hydrodynamic time step is being reduced to help out that linear solver. So the new option, by using this nonlinear solver, has the potential to avoid this time step reduction and maintain stability and speed, even if temperature changes are large in the calculation. To enable this feature, you go to Numerics, Solver Settings, and then you can check the box for Enable Nonlinear Fluid Temperature Solver. A second option that we've added is targeted at speeding up simulations with very fast chemistry. This option is on the top level chemistry window, and this is a reaction rate limiter based on the volume ratio change of species in the fluid domain. And this is a cell-by-cell operation that happens in the sense that the reaction rate limiter is applied only to cells that are exceeding this maximum ratio change that you specify in the GUI. So when the reaction rate limiter is active in a cell, all the reactions within that cell are limited by the same factor in order to maintain the relative reaction rates across the whole set. This option has the potential to significantly speed up your simulation if it's showing messages like this one, which say decrease DT chemical mass production in cell. Depending on the specific chemistry being solved, this new option for limiting the reaction rates may significantly change the calculated reaction rates, and therefore could also change the dynamics and the spatial extent of the material consumption or production from that chemistry. However, it does have the advantage that it can avoid kind of this full system hydrodynamic time step reduction due to very fast chemistry in just a small number of cells. And we'll talk about this a little bit more during the demo portion as well. But the benefits of the faster solution time should always be weighed against the possibility for a loss in accuracy in those few cells that might have the really fast chemistry. And the decision of whether or not to use this option should be made on a case-by-case basis to make sure it's appropriate for your simulation. As an example of using these two new options, the nonlinear temperature solver and the chemical reaction rate limiter, I've run the gas-fire training problem in two configurations, and we'll look at the results here. I'm calling the first configuration case 1, and it uses the default settings that we've always had in Barracuda, which is to say the time step adjustments are left in their default states so that the solver will lower the simulation's time step if the maximum temperature change limit is exceeded or if the maximum fluid mass fraction change from chemistry is exceeded. By comparison, in case 2, I've disabled both of those options, but I've enabled the new options for the nonlinear temperature solver and limiting the reaction rates based on the fluid phase volume ratio change. Keep in mind that this is purely an example to illustrate the potential for speed up, and the amount of change that you would see in your own simulation will be strongly dependent on the specific chemistry you're solving and the conditions in your system. Both of these cases were run out to an in time of 100 seconds, and they were run on a Linux machine with an NVIDIA RTX 4090 GPU card. Case 1 took about 2.1 hours to reach 100 seconds of simulation time, whereas case 2 finished in about 1.3 hours, and that's about 62% of the total time it took for case 1. So definitely a speed advantage here by eliminating those time step reductions. For case 1, we were seeing a lot of time step reduction warnings related to the chemistry mass production. I think that was dominating for this particular simulation. There were also a few warnings related to the large temperature changes. So the default time step limiters were kicking in, and they kept the time step around 2 milliseconds for most of the simulation. By comparison, case 2 did not have these time step limiters enabled, and instead it was able to run stable and fast by using the nonlinear temperature solver and the chemistry rate limiter features. This was able to maintain a time step about 4 or 5 milliseconds on average, and so it was able to run faster. And in this case, we reviewed the simulation results. We didn't see any significant or major differences in fluidization behavior, temperature, gas species compositions, all of those sorts of things. So in this case, we could make the argument that, okay, great, running at this higher time step is acceptable, and we get a good speed advantage. So in this case, it's a good combination. If you're going to use this, we definitely recommend testing these features out on a case where you have some basis for comparison with previous simulation results or experimental data, for example, so that you can quantify any change in the solution accuracy and make an informed judgment about the trade-off between simulation speed and accuracy. In addition to the enhancements and the new options that we discussed about Barracuda itself, we've also made a few changes to the bundled Tecplot for Barracuda post-processor that we hope will be helpful for people. The first change is that we've alphabetized all the variable lists that you see in Tecplot for Barracuda. This will make specific variables a lot easier to find, especially for simulations that have a lot of variables going out to the visualization files. Keep in mind, or make note, that the XYZ position variables and the IJK cell index variables, we put those so that they're always at the top of the list, and then all of the other variables are alphabetized after them. Another change we made is to have all layout and style files reference variables by name instead of variable position or index. This change should help to make the layout and style files more reusable when you copy them from one case to another. And then finally, we've updated to the latest stable release of Tecplot, which is 2024 R1M1. Okay. At this point, I'll go ahead and drop out of PowerPoint, and I'll switch over to a quick demo of a few of these features. So here, I'll go ahead and open up version 25. And the first feature I want to talk about is the new wall impact features. Just so you know what the case is that we're looking at, I'm using the CFB erosion supplemental training example, and this is available on the CPFD website for users to download if you want to look at a system like this. In this case, I'll go ahead and close that. We've enabled several wall impact models, and this used to be called wall erosion in the GUI. So be aware, we've kind of made the label a little bit more general because now, in addition to erosion models, which here we're using the OCA erosion model. We also have this liquid accretion model. So that label has been changed to just wall impact. You'll see that there's this manager here now, and this is similar to other managers throughout the Barracuda GUI, where you can add, edit, delete, those sorts of things. And one thing I wanted to mention is if you were using the erosion model from a previous version of Barracuda, it will come through to this version, right? And it will still be enabled. It will still work. The same capability is still there. To make it clear what this is, we've named it legacy erosion. So this is the erosion model that has been in all previous versions of Barracuda. And if you look at the legacy erosion model, there are some default values that were in Barracuda already. If all that you did before was enable the erosion model, these are the values you would get for wall parameters and particle parameters. We also did a little bit of work to make it easy to put in wall parameters for aluminum, glass, steel. So those are kind of built in. And then of course you can go user defined, and then all of these text boxes become editable and you can put in your own parameters. So this is what legacy erosion looks like. Liquid accretion is actually, it doesn't have any user definable parameters, so be aware of that. This is not a mistake. This page was intentionally left blank. And then finally, OCA, if you go into this, you'll see that in the OCA model, this is kind of similar to the legacy, but with even more materials to choose from. So OCA and their co-authors gave a lot of parameters for metal materials, aluminum, steel, iron, those sorts of things. So you can select those for the walls. And then for particles, we have a few particle materials here, or you can go into user defined mode. And again, these text boxes come to life and you can start defining your own parameters if you know these values for your specific material. The other thing that you'll see, and I'll go ahead and drop out of this one just to show one of these ones that's already defined. You'll see here, what we did is we made 3 models that are all using the OCA erosion model, but they're in different locations of the system. And so if we go to set cell region, this particular one is for the main boiler vessel. So we're selecting just the region that encompasses that part of the system. The second one is just the cyclone. The third one is just the fluidized bed heat exchanger. And what we found is in some projects, it just makes it a lot easier to visualize the particular area of interest. And so that's what we'll show here. If we look at post run, we can go to view results. And this default view is the same as it's always been, right? You're going to get the most recent solution time, and you're going to see a view of particles colored by volume fraction. But here we'll double click our quick macro panel for walls impact, and we'll see that this changes the view. And really now what we're seeing is the walls zone, and it's being colored by the amount of wall impact calculated for model 001, which in our case was just the boiler vessel. One thing that I see quite a bit is that there are usually some regions within the vessel that have like really high wall impact values, right? And then everywhere else is relatively pretty low. So if you take the default view, you will see the highest regions of potential erosion. However, sometimes it makes it hard to see other things. So you may need to double click this contour legend and adjust your levels to kind of bring that down a little bit. I think on this one, I've been seeing that something like 100 to maybe 2000 kind of gets us a little bit more visible results. That might be a little bit more easy to see where these regions of high erosion are. And then if you want to see the other regions, right? So now we're seeing your erosion just on this boiler vessel, but we can always select the other impact models from our list, right? So we can go wall impact 2. This one is going to start showing results on the cyclone. Wall impact 3 is going to start showing results on the fluidized bed heat exchanger. And again, adjust the limits so that you start seeing things maybe a little bit more clearly than the absolute maximum limits might give you. And the nice thing about this is, within Tecplot, you could potentially make 3 frames in this case and show the erosion from each spatial region and have a really nice visualization that's easy to communicate these results to other people. Okay, the next thing I'll show is the user-defined expressions for boundary conditions. And I think people are going to find some really nice uses for this. This is a really powerful and flexible feature, especially if you start getting into complex geometries. So here, let me go to View Setup just so we can see what this example looks like. And since a lot of vessels that people simulate in Barracuda are cylindrical, this example is just focusing on kind of cylindrical coordinates and how you would do things like this. As I mentioned in the presentation, this UDE functionality is available for all of your boundary conditions that attach to faces, right? So this would be pressure BCs, flow BCs, thermal wall BCs, and then also for the erosion models or the wall impact models. So all of those have the same interface for defining this. And in this example, we'll just show a few things to kind of give you an idea of how this works. The first that we'll look at is a pressure BC that's defined as a circle on the top of this vessel. Then we'll look at a flow BC that's defined as a ring at the bottom. And then we'll talk a little bit about this heating coil in the middle that has a thermal wall BC. So here, if we go to our pressure BCs, one thing I definitely want to emphasize is that everything in this locations tab works together, right? So first, you'll probably still want to go in and do a set cell region. And in this case, the set cell region is saying, okay, I only want to consider faces on the very top surface of my domain, the main cylinder in the domain. So that automatically limits it to only these cells in that top layer. Okay, and then the direction says we only want to consider cells in the Z direction. So that requirement is applied as well. And then finally, you get to your user-defined expression. And for cylindrical domains, I think this is going to be a really common pattern that people will need to know about, right? So basically, for every cell in the system, these equations are going to be evaluated, and the solver will decide whether that cell meets the criteria specified in this equation. And so we're going to calculate for every cell, what is my radius from the center? So cell center X, cell center Y, and we're using just traditional geometry here. And so we calculate a radius, and then we're telling Barracuda, return a non-zero value if my radius is less than or equal to 4. And what you'll see is, depending on what you return here, if you return a 0, then that particular cell is not selected for the boundary condition. And if you return anything other than 0, that cell is selected for the boundary condition. So this less than or equal to, it returns a 1 if this criteria is met. So by doing this, we're selecting any cells with a radius of less than or equal to 4 for our pressure BC. You'll see here, and I hope this makes sense to people, like, we're still selecting kind of full cells that meet this criteria, right? So you'll still see a Cartesian outline to even this sort of cylindrical selection. But that's okay, right? I mean, this is still much, much easier than what you would have had to do to get the same result previously. And you're always going to be limited by your cell resolution to how smooth that will look. Okay, so this example is like, how would I do just a full circle? The flow BC is more of a ring, right? So again, we select our region. In this case, this is the layer of cells at the very bottom of the system. We're doing normal to surface. I think Z would actually give us the same result in this case, since we're going to be selecting things that are away from the walls. But again, we calculate our radius for all of the cells. And then in this case, we're going to return a 1 if my radius is less than or equal to 2.5, and my radius is greater than or equal to 1. So by doing that, we can get this outer radius is 2.5, this inner radius is 1, and here I'll try to change this so it's a little easier to see. But yeah, we're able to select only the cells that are in that the ring rather than outside of it or inside the inner circle. Finally, let's take a look at this heating coil. And in this example, I apologize, thermal wall BCs. In this example, what we did was we defined an inner radius of the coil and an outer radius of the coil. So if you knew that for some reason your shape had different behavior on the inside versus the outside, you could definitely do that, right? So again, this one uses face centers rather than cell centers. I think most of the time you'll get almost exactly the same result anyways, but just be aware those are available. This one says, okay, if my radius is less than 3.6, put this thermal wall BC on there. And in this case, the select cell region that we started with was kind of not touching the very top of the vessel and not touching the very bottom of the vessel. And so that's what we're starting with there. By contrast, the outer radius is kind of similar to a ring. We only want to get things that are greater than 3.6, which was our inner radius, and less than 4.5 so that we don't get the outer wall of the vessel, right? So this sort of UDE makes it pretty easy to capture really complex shapes. And here I'll show this through the zone style. We do have, we'll show the first one. So this is our inner radius. It's only touching that inside surface of the coil compared to the outer radius. And that's a little trickier to see, but it is only touching kind of the outside surface of the coil all the way up. Yeah. Oh yeah, and if we look kind of from a top view, I'm going to turn off the pressure BC just so we can see down on it. Yeah, there we go. So that makes it a little bit easier to see outer surface versus inner surface. So yeah, hopefully this makes things really flexible for people and just avoids the need to define a lot of flow BCs or pressure BCs or thermal wall BCs in order to capture these complex shapes that you might be encountering. Okay. The next thing I'll talk about is the nonlinear fluid temperature solver and the chemistry rate limiter. So here I'll go ahead and open up that gas fire project that I had run for that example. And there's not a whole lot to show here, but I do want to just remind people kind of where these are located within the GUI. So if you want to use this chemistry rate limiter, this is on the main chemistry page. By default, this is off, right? So if you want this to be in effect, come in here and check this box. The default maximum ratio change that we put here was 1. This is kind of just what we think should work pretty well most of the time. But of course, feel free to try different values to see if that works better for your system. One thing that to be aware of is in the current way that the solver is working, it does not output a specific message if this goes into effect in a certain cell. So you can't really tell which cells are being influenced by this setting. So just be aware of that. It's a little bit of a difficult to know where that's happening. Okay, and then if we go to numerics, solver settings, this is where the nonlinear fluid temperature solver lives. And again, this is by default, it's not enabled. So if you come in here, you can enable it. This follows the same iterations and residual pattern that you see above. So here we're saying, okay, nonlinear solver, we want you to take a maximum of 20 iterations. And in order to be considered as converged, we want you to get within 0.1 Kelvin of the correct answer. So that's what these parameters are telling you there. And then the other ones that I had disabled, those are under time controls, right? So if we go to advanced time step settings, I disabled these two, maximum temperature change and maximum fluid mass fraction change, in order to totally eliminate them from reducing my time step. One thing to note is that it could be useful, instead of just totally disabling these, you could potentially just increase their values as well, right? When you enable this nonlinear temperature solver, for example, theoretically it should be able to handle much larger temperature changes than the linear temperature solver could. So you might say, okay, instead of a 300 Kelvin maximum change, I'm willing to let the solver go up to a 600 Kelvin maximum change before reducing my time step, right? And this could still have a big advantage for your simulation, and it might be a useful way to go. Kind of similar to the chemistry, right? You could potentially just go to larger values here and still get a good advantage by using these features in combination with the new features that have been added. So the way that I did it is not the only way that you could think about it. Okay, and then finally, let me go to post run. I just wanted to point out, if we go to Tecplot, oh, and actually before I go here, the visualization alphabetical order thing is really related to the visualization data that you select in this window of Barracuda, right? So we're saying, okay, these are the things that we want to output to all the Tecplot files. And specifically, a few of these things are like one line here, but they turn into multiple variables in Tecplot. So if you say, I want my chemical reaction rates, Barracuda is going to give you the rate of every reaction into Tecplot. So you're going to get 9 variables out of that. If you say that you want your gas species mole fractions, then you're going to get a variable for all of the gas species here. And if you say you want your particle materials, you're going to get a variable for every particle material. So just be aware, even though this list looks kind of small, it can potentially turn into a big list in Tecplot. And that's what we're seeing here. So that list that we selected turns into 71 variables in Tecplot, especially when you turn on time averaging. So that's where this alphabetizing really becomes useful, is that it just makes things a lot easier to find. So here, if we kind of just scroll through this list, you'll see X, Y, Z, I, J, K are always at the top, and then we start alphabetizing things. So a lot of fluid material kind of data will all be together. A lot of particle material data will all be together. Rates of reactions will be together. All of your time average variables will be together. So I think this is going to make things a lot more efficient for people who are working with the results on a day-to-day basis, and just make it a little bit faster, save you a few seconds every time, and hopefully make your day a little bit better. Okay, I think those are all the things that I want to do demo for the moment. So I'll go and turn it back over to Rosemary now.
All right, well, thanks, Sam. Now that we've covered all the new features in Barracuda version 25.0, I encourage everyone to submit your questions. We'll be answering those questions in just a few minutes, so be sure to get yours in that question panel. And while you're doing that, I'll point out a few different ways that you can get started working with CPFD. So software licensing is the first option, where your team uses Barracuda directly to set up, run, and post-process simulations. Virtual Reactor can be run on your own hardware or on the cloud, and global teams can take advantage of our global enterprise license option available in most countries. We have a number of different licensing options available, so contact our sales teams for specifics. And if you're already a Barracuda user and you'd like to learn about adding license tokens to run more simulations, or maybe you're running single GPU and you'd like to take advantage of the speed up of multi-GPU, please contact our sales team as well. It's very easy to add solver, chemistry, and or GPU tokens at any time to meet your needs. We also offer engineering services for customers seeking the engineering benefits of modeling their system with Virtual Reactor, but who might not have the capacity or in-house staff available to do so on their own. So you can also contact us if you want to learn more about this option. And if you're eager to get started using Barracuda hands-on, attending one of our web-based engineer-led training classes is a great option. Our next class is coming up in June, and we'll have more information about that in a few slides. And training can be combined with project work and licensing through our Quick Start program, which is intended to get you up and running as quickly as possible. CPFD sets up and runs the first model for you, and then we hand it over to you, train you on the software, and then provide the software licensing. This allows you to build out your own in-house capabilities with the model that's already up and running. And finally, we work with people in a variety of custom ways through R&D partnerships, and this can be direct with us or collaborative with our other strategic partners. So contact us if you're interested in becoming a partner. So we have some upcoming events that we'd like to highlight. CPFD regularly schedules web-based training classes for people interested in learning about Barracuda. And so please contact us if you'd like to join either of our upcoming classes in June or August. Also in June, PSRI will be holding their annual meeting in Chicago, and CPFD will be in attendance, and we look forward to seeing a lot of familiar faces from the fluidization community at that event. And now we're ready for questions. So be sure to add any questions you might have into the question panel if you haven't already. And so I'll start. I'll ask the questions. Sam, you can answer them.
Okay.
Okay, so if I had the old erosion model enabled in my project, what happens when I open it in 25?
Yeah, so as I showed in the demo, basically this will get imported. It'll be called legacy erosion, so just be aware of that. That's the name it'll have. And it will import any settings that you had in terms of the angle dependence or the velocity exponent or mass exponent of the particles. So yeah, those old erosion models are completely supported. And then you can also add other erosion models to that same project. If you wanted to see what was the difference if you used Oka erosion, for example, you could do that.
Okay, yeah. And so you showed a moderate speed up using the new chemistry and thermal limiters. Is that typical, or would a fast reaction, for example, combustion in a small local zone, result in bigger speed ups?
Right, yeah, and so, yeah, keep in mind, this is totally system dependent. So if you have different chemistry, especially like combustion chemistry, you could see something quite different, right? Your speed up might end up being something like 10 times faster or even 100 times faster, depending on how much your time step was being reduced. So one example that you could think about is, let's say you had like a natural gas injection and that was a fuel source that is combusting to provide heat. But let's say for your specific simulation, the exact dynamics and the spatial profile of the natural gas combustion are not really critical. Like in some cases, all you care about is that you get the right amount of heat into the system and that you do combust all of the fuel, right? And that would be good enough, even if that combustion was spread over a few more cells or it took a little bit more time to happen. So in a case like that, you can definitely use this chemistry rate limiter. And as I mentioned, like the spatial profile may not be exactly right, but if that's not your main focus of the simulation, then you could get, a 10x or 100x faster simulation and be much more useful, much quicker to iterate on by using that. On the other hand, if that simulation was really focused on the detailed behavior of the natural gas combustion and you really cared about the dynamics and the spatial profile of how the natural gas was combusting, then don't use the chemistry rate limiter, right? Like in that case, you kind of have to run at a really low time step and just accept the fact that the simulation speed is probably going to be pretty low to capture those really, really fast kinetics.
Okay.
Kind of related to that, I see this question.
Okay. Can you show which cells are restricted by the volume ratio setting with Tecplot?
Yeah, and in this case, you can't, like currently at least, right? With this release, we've allowed you to enable this feature, but there's no visualization data output that would be able to indicate where is this happening or to what extent. So I think that's a very valid like feature request for the future. But yeah, currently in this release, it's not possible.
Okay, thanks. Can I put two erosion models in the same location to see the difference between those erosion models.
Oh, definitely, yeah. And in this case, I showed an example where I was specifically using different locations only to illustrate that sometimes it's useful for organization in that way. But yeah, you can definitely overlap erosion model regions. You can use exactly the same region. There's no limitation on how that can work.
Yeah, it's very flexible. Yeah. Is there a way to create batch movie scripts for slice animations? Like for a particular time step, I'd like to see the Z slice moving from the bottom to the top of the model. And I have a number of style files that I would want to automate.
Oh, okay. I bet this is possible to do. I don't think it's possible with batch movie itself, which is a utility script that we ship with Barracuda. Like that script, it is specifically focused on creating transient animations that progress through time. Whereas this question says, okay, I have one point in time, but I want to automate the animation of this. So yeah, I'm almost sure that you could do this with like a macro in Tecplot or something, because I know you can do it in the Tecplot GUI. And so I bet there's a macro that can accomplish that as well. So we will contact you and take a look at that specifically. But yeah, Tecplot has so much flexibility, right? You can connect to it with PyTecplot, you can connect to it with macros and run things like that. So yeah, for most of these types of automation tasks, it's usually possible to accomplish things pretty efficiently.
Yeah, well, thank you. I think that's all the questions that we have for today. So I think we can end this webinar at this time.
Yeah, thank you all for attending, and we hope you enjoy this release of Barracuda.
Yes, thank you.